Good afternoon, everyone. We're taking a minute to get everyone in out of the waiting room, and then we'll start. All right, why don't we start? We're a few minutes in, and others will join, I'm sure. So first, everyone, welcome to MaRDA 2026. This is actually the sixth annual meeting of the Materials Research Data Alliance, which is kind of amazing to those who have been here from the start. We started at some point in time in a data summit at the Big Ten Center outside of Chicago with a quote from Alex Saleh that said, "No scientist ever wanted less data." And maybe that also applies to AI these days. And so we're really excited to be here with a number of really great sessions, I think, to talk about community work and stakeholder work and how we can advance things in the data world and then data as foundational for the AI world and how we share models and how that is transforming things. So we have a great series of sessions on tap. I don't want to spend too much time on anything before that, but I really want to thank the Governance Council, which is shown here on the right. Everybody's names are very small, but these people meet monthly to keep this going. They're all volunteers, except for Selena Fitzgerald, who we thank especially as our part-time communications specialist here in MaRDA, who has made a lot of things work, and our technical specialist, Austin Tremblay, who joins us every year for the annual meeting and is working in the background to make all this happen. We also want to acknowledge support from the NSF. In a part of MaRDA is a research coordination network from the Pharos program within OAC and helped by DMR, and a NIST award that has been with us in various incarnations from the start to really help us continue going as well. So there are shared notes and question docs for those of you who are new, or those of you who have been before. You'll see that we share notes and docs in open Google Docs that everyone has access to. We've put the short links there. I'm sure Selena is copying and pasting those links into the chat for you, as well as the full link for those who don't have access to Bitly. The pattern is simple this week. Every session is numbered on the agenda. We're going to go into session 1, and it'll be Bitly MaRDA 2026_1. The next session will be _2. Tomorrow's sessions will be _3 and 4. You can figure it out from there. I also want to say that the meeting is being recorded if you didn't notice that when you first came in. And that means that this content will be posted on the web after the meeting. If you don't want your comments posted openly or your voice posted openly, then please participate only in the Google Doc. But the way we work is that we'll have panel discussions on a number of different interesting topics, and then questions to the panel, including reading questions out from the Google Docs. This year's meeting is notable because we have 425 registrants this year. So we have grown yet again this year, despite a lot of complicating things during the year to make it. And so I think that the need for MaRDA, the need for the network, and understanding how we put things together continues. Our mission basically remains the same, that we focus on connecting and integrating research and translation of that research through data infrastructure to really realize all the way that we can make interoperable materials, data, and AI. And so MaRDA is here to really promote that convergence of ideas and people and data. And we're going to look at that this year in a theme that really focuses on the new focus that we see in lots of programs towards translation, towards making the bridge from fundamental and basic research out to actual applications, design, and implementations. So you'll see that we have a number of different panels this week that focus on industries. Our first session will do what we often do, which is bring in those from agencies that are helping to drive this work from above and talk about the interagency work, things that have traditionally been done by the MGI subcommittee, and Jim Warren from NIST, John Schlueter from the NSF, Sean Donegan from the Air Force Research Lab, and Andy Schwartz from DOE will give us a lot of insight into that. So we'll start that panel in a minute. We then have a great poster session. We have had, as a hallmark of the MaRDA meeting over the years, a number of really terrific student and postdoc posters. We've changed the format this year out of GatherTown and into 4 waves, but there'll be an explanation of that before the poster session starts. We have a poster session today and a poster session tomorrow. And then our second panel today will be the first dive into the materials industry and the emergence of data-driven AI. And we'll talk about that when we introduce that panel. So without further ado, I'm going to stop the share and we'll bring in our panelists. And Juan Verduzco from Perdue, who is a research scientist there, will introduce our panelists. And I will step aside for a few minutes. Juan, are you ready?
Yep.
Dave, before the introduction, I just saw a post to the chat that seemed rather urgent to deal with.
Selena, can you grab that?
Yeah, not the one about the metadata,
Yes.
but there is metadata problem with the date.
Yeah, and I had the same problem with the link.
Yeah.
Yeah.
All right.
So there could be some
Thanks
people
for that. I know the one that came in the email from Eventbrite was right, but Selena will step out and message people and let them know about that, I'm sure.
Yeah, because we're at 83 of the 400 and some. Right?
Yeah. We don't expect to have all 400 at the same time. This panel usually gets the biggest turnout, and then people come to specific things they want around their teaching or work schedule of whatever type.
Sorry to interrupt. Carry on.
That's all right. Juan, why don't you go ahead and introduce the speakers, and I will go blank for a second.
All right. So good afternoon, everybody. I'm happy to be moderating this first panel and welcome you all to the opening panel of MaRDA 2026. Thank you for being here and for starting the meeting with us. So in this panel, like Dave Elbert said, we're going to offer the community a chance to better understand how materials data and AI are shaping national strategy and how our community can contribute in ways that advance both science and strengthen the agency missions. So as an introduction, I'd like to thank our panelists for joining us. They're going to be doing some presentations. So we're going to keep all the questions to the end, and you can always write your questions in the Google Doc, and we'll make sure that we address them or combine them with similar questions so that the panelists have a chance to address them. And we appreciate the panelists' time. We appreciate the panelists for taking the time to share their perspectives with the community. So to start, we're going to start with Dr. James Warren, who is the director of the Materials Genome Program in the Materials Measurement Laboratory at NIST. In 2010 and 2011, Dr. Warren was part of the ad hoc committee with the Office on Science Technology Policy in National Science and Technology Council that crafted the founding white paper on the administration's, at the time, Materials Genome Initiative. And since 2012, Dr. Warren has served as the executive secretary of the NSTC MGI subcommittee and all of the successor entities, coordinating interagency efforts to achieve the goals laid out in the MGI. He's a fellow of the American Physical Society, the ASM International, and the Metals, Minerals, and Materials Society. So with that, I'll give it up to Dr. Warren.
All right, thank you. And it's always great to be here and see how far MaRDA has come and the ongoing influence that it's had on the community. So I'm now showing my slides, so I can't see anybody. So hopefully this all works smoothly. Otherwise, break in and let me know I'm talking to myself. So very quickly, I'm going to go through sort of my own perspective and this perspective on accelerating materials innovation through data and models. I'm not going to spend a lot of time, of course, on the MGI, but I will give a hasty look back just to sort of set a little context in a couple of minutes, and then sort of talk about how we're kind of thinking about things now. So if we look back at the MGI, I pulled up this slide. Maybe a couple of you have seen this, but I had to use the Wayback Machine because you can't find this website any other way. So this was from the Center for Theoretical and Computational Material Science at NIST that we set up back in 1995-6, just a couple of postdocs, including myself. And one of the things that was interesting to me about this was the mission that we had at the time for the CTCMS, which is still around. It has a number of elements to it, but the last bullet is what I'm focusing on here, which was to develop powerful new tools for materials theory and modeling and accelerate their integration into industrial research. And so we really believed right from the outset here that it was very powerful if we could share not just archival papers, but actual code. And in my mind, that was really one of the reasons when the opportunity for the MGI came along. I was sort of primed by my experience at NIST to really jump into that effort. And there's this great slide that Tressa Pollock put together now more than 15 years ago, really sort of outlining the history of the MGIs in terms of government policy, if you will, and various programs. So it's, as an idea, of course, it's really been around for a long time, which is this sort of notion of how do we create the so-called materials innovation infrastructure, which is detailed in the sort of that circle Venn diagram in the lower right corner. But the pedigree of the MGI, you know, is multi-agency and goes back, you know, into the misty era of the 1980s, if not before, and really was at the time about elevating modeling and data to sort of more of a peer with experiment, which really was the dominant paradigm, of course, material science, because the problems were so hard. And so when the MGI gets stood up, you know, NIST then had to focus on how it would support the initiative. And we decided to really focus on the sort of digital objects, that is the data and the models that make up the materials innovation infrastructure. And how do we move that information around that's enhancing and enabling an exchange? How do we make sure that the quality is the highest? And then, of course, what are the methods and metrologies that we can build off this infrastructure? And so this really leads us directly to data-driven analysis and models. And, you know, the vision of the MaRDA really grows out of a lot of these ideas. And the notion that we needed to create forum within, you know, amongst academics and industry to really determine, you know, how do we get to the vision of data-driven analysis? And so, you know, we were using the expression data-driven back in 2013. Now we would just say AI and be done with it. There's obviously a lot of effort in other agencies. You're going to hear from them today. And although I don't have Genesis, I think, up here, obviously, that's an example we're going to hear a great deal about. And there's a lot of effort across the service branches. So in terms of, you know, where the MGI has brought us to today, I would say, you know, that we're at an interesting sort of cusp, right? There was a lot of success in the MGI, you know, with high throughput DFT, and there was a lot of success that sort of came out of the integrated computational materials engineering community. Like, you know, you can see like SpaceX developing new materials 10 times as fast, new alloys for the US Mint for the nickel. The successes in ICME were really in metallic systems because mostly of the capability of using CalFAD, which was rapid, cost-effective materials design. For polymer systems, however, it remains challenging. And in general, you need substantial domain expertise for any application of ICME. And modeling in general is still too slow, and we need to speed things up. And of course, the answer to that is that we need data so that we can create AI models. And we also need incentives for data sharing. And we've talked about this sort of ad nauseum within the context of MaRDA and in many other venues. But right now, the incentives still remain rather elusive. So to take advantage, as I said on the last slide, of AI, we really need more materials data. And so how do we get more? And I think we're going to end up talking a great deal about this over the course of the next few days. Right. So the MGI developed many new materials, but inserting those materials into manufacturing remains challenging. So self-driving labs can not only deliver targeted materials, and I think everybody sort of appreciates the fact that they can do that, but in my mind, one of their key functions is that they generate vast quantities of data, and that data itself can be used to create surrogate models of materials, processes, and properties. And those can be substituted for traditional physics and chemistry models, which are often too slow. These surrogate models are essentially effectively materials digital twins, which can now operate at the speed of manufacturing. And then that allows us to insert knowledge of materials into the manufacturing paradigm. So I actually honestly believe that we are at the cusp of finally taking a lot of what I would consider to be low TRL, TRL 1, 2 type research, and actually being able to accelerate all the way up the value chain, which was the original vision of the MGI. So it's an exciting time to see that vision coming to reality. And I look forward to hearing from my other colleagues on the panel.
All right. Thank you, Jim. All right. So let's go to our next panelist. Our next panelist is Dr. John Schlueter, who joined the National Science Foundation in 2013 as a program director in the Division of Materials Research, in the Director of Mathematical and Physical Sciences, where he manages the DMREF program. DMREF is the primary program by which the NSF participates in the Materials Genome Initiative. He's also a program director for the Materials Innovation Platform and the Programmable Cloud Lab programs. He was elected as a fellow of the American Physical Society in 2015 and received NSF's, I don't know how to pronounce that, MSF Meritorious Service Award in 2022. So take it away.
Well, thank you. Hopefully you can see my slide and presentation mode and hear me okay? We're good?
Yep.
Okay, thank you.
Yep.
So thanks to Jim for that introduction. We really kind of needed that to put my talk in context with respect to the Materials Genome Initiative. But my short presentation here will highlight some of the activities that are going on at the National Science Foundation relative to the interests of MaRDA. And so there's a lot going on at NSF right now. You may have heard that we're moving to a new building, new headquarters building soon. So you can see the picture of our new building there. And probably the other major part of NSF that's happened recently is a relatively major reorganization that we are working through now. But I'm not going to talk too much about those activities at the moment, but rather move on to some programs at NSF that are relevant to materials data. And so probably foremost in my heart at the moment is the DMREF program, Design Materials to Revolutionize and Engineer Our Future. So this was NSF's primary and probably largest response to the Materials Genome Initiative. It's been around for a little bit over a decade now. You may be aware of the DMREF program, but really it's always been designed to bring together design, discovery, development of materials through harnessing the power of materials data. And the data aspect has been growing over the years. The data management plan has always been a key component of DMREF proposals that we evaluate probably more strongly than most other programs at NSF. So the data management plan is critical. And we bring together a community of scientists that across many disciplines, theoreticians, experimentalists, synthetic folks, statisticians, mathematicians, data scientists, etc. So these DMREF projects are small team awards, typically 3 to 5 PIs per project. They're for 4 years and have a budget of approximately $2 million. Over the years, we've seen a large increase in the number of proposals that include artificial intelligence. At the beginning of the DMREF program 12 years ago, very few proposals talked about AI, machine learning in their proposals, but over each successive competition, this has increased, and we're probably up to about 70% or so of proposals that include AI. And so if you want to learn more about the DMREF program, you can look at this National Academies report from a few years ago that kind of give us some perspective on where DMREF has been and where we would like to go. DMREF is a biennial competition with the next competition expected in 2027, next year. So with respect to the previous competition in 2025, we made 25 new awards that were announced September 9th of last year. This includes about 104 principal investigators, 44 universities, and 25 states, or half of the U.S. as far as states go. We also emphasize our federal partnerships. You can see the various partners that we have here: Air Force Research Laboratory, Department of Energy, NIST, ONR, and the U.S. Army, DEVCOM. And most recently, in the last solicitation, we've partnered with 4 countries: Canada, Germany, Israel, and India, to really work more efficiently across international boundaries to learn the best practices with respect to, I mean, everything materials, but certainly including data sharing, AI, and various expertise like that. So if you're curious about the awards that we made, you can go to the demref.org website and find them under the 2025 award webpage. So we also, in the years that we don't have DEMREF competitions, we have MGI PI meetings that bring together MGI-related efforts across the various federal agencies. And I'm not going to go into this in great detail, but the meeting that we held in 2024, we offered 6 challenges actually to our PIs for various things that we'd like to see improved in the DEMREF program. And one of these included the Fair Data Challenge. And so the idea here was really to challenge our PIs to be able to use existing digital data that was not generated by the immediate group that wanted to use the data. And I think that's kind of a real challenge for the field, or at least for the DEMREF community, is that they're usually pretty good at sharing within a small team, but sharing across teams is more difficult, and really making data fair. You really need to take this data for a test drive and see whether others can really use your data. So we challenged our PIs to do that, and to look for partners that they could work with, and to try to use their data and to develop new tools for data intensive research that bring together multiple teams, PIs, institutions, etc. And so one example of that, I just threw in a couple highlight slides here, was a Hacktive Matter hackathon that was held by one of our DEMREF teams. It also brought together our Bio-Pacific MIP that I'll talk about shortly, and 2 other DEMREF teams for a 2.5-day hackathon at Santa Barbara. This group really got together and talked about how they can share data, learned how to share data, to develop new tools, etc. Really in the area of active soft matter. And so there will be another one of these Hacktive Matter hackathons coming up this year. So if you're interested in that, it's going to be held July 19th to 21st at UCSB. And DEMREF is certainly not the only program at NSF that's relative to MaRDA, but also the Material Innovation Platforms, or MIPS. These are larger platforms or center scale programs that embrace the philosophy of MGI and really work to engage the emerging field of data science for materials research. And so we've had 2 sets of these MIP platforms. The first of them was centered on these, mostly layered 2D type materials. And one of these is 2DCC, and the other one is Paradigm, that's at Cornell and Johns Hopkins. You can kind of read the descriptions of the programs there. This is from the 2016 class. And then the second class was from 2020 that's focused on soft materials and biomaterials, and that is the Bio-Pacific MIP and Glyco MIP. There is a new competition underway. So these are proposals that came in from 2025. And these proposals are currently under review, but are really in the areas of amorphous matter and composites, etc. So the results of that competition will be revealed soon, we hope, later this year. An example from the kind of what these MIPS are doing is, for example, this lifetime sample tracking data management system that 2DCC has developed. That is really this data storage system that's been developed to be able to capture experimental data on samples that are synthesized and characterized at 2DCC. And currently, this is a database of over 18,000 bulk crystals and thin films that were produced at this facility. So you can have the link there to the LIST data management system. But this is the sort of data intensive capabilities that these MIPS are developing. Another program that's relevant here are the artificial or AI institutes. And we're proud to announce the newest AI institute, which is Artificial Intelligence Materials Institute. This is centered at Cornell and really is focused on data-driven optimization of film growth through self-driving laboratories. and they're focused on three classes of materials, these 2D moire structures, new superconductors, and soft functional materials. And so really the AI Institute has two parts. One is to advance the AI component of the center, and the other is really for the more topical area of discovering new materials. So again, you have the link there if you'd like to learn more about the AI Materials Institute that we're supporting. Another program that's quite relevant are the programmable cloud labs. And I see that Alex Vedati is, I think, here in this meeting as well. And so they held a workshop a couple of years ago. I don't think I have the date written down here, but on creating a national network of cloud laboratories and self-driving labs. And this led into the development of a solicitation for programmable cloud labs. And these laboratories have the characteristics of having AI in the loop, these bespoke programmable laboratory workflows, remote access to the facilities, and various collaborations. And so these proposals are currently under review, but if you're interested in kind of in the legislation that goes along with these programmable cloud labs, you can look up the bill that is currently hopefully working its way through Congress, is S3468, to hopefully create a national network of cloud laboratories. And so NSF is moving forward in that direction as well through the TIP directorate. And then I wanted to call out, I think this is more or less my last slide, is the few additional data relevant programs at NSF, CSSI, which is Cyber Infrastructure of Sustained Scientific Innovation, that has been around for a while. There's really three flavors of this, the elements, framework implementation, and translation to sustainability. You can read that on the slide there. The CSSI are really not research proposals, but these are really more for development of infrastructure. And corresponding complementary to that is the CDS&E program, computational and data science and engineering. And so these are smaller proposals that must have a significant component of computation or data science that goes beyond what you would typically find in other NSF programs. And with both of these opportunities, I would consider you to very closely follow developments in when the new proposals will be deadlines for the new proposals and any changes in those solicitations, because we do expect changes based on the reconfiguration of NSF. So they hopefully will still exist, but just follow the webinars and various announcements on those. And then finally, I guess this is my last slide, is the future of AI and MPS. Many of these initiatives or programs begin with workshops that work their way eventually into solicitations and then to real programs. And so a workshop was held last March at MIT, looking at the future of AI in math and physical sciences. And so you can find this workshop report that's now accepted for publication in Machine Learning, Science, and Technology. And it really emphasizes how to enable both AI and MPS research, how to build an interdisciplinary community of these researchers, and of course, to foster the education and workforce development of AI in MPS. And I think with that, I will stop and can go further if there's questions.
All right. Thank you so much, John. We're going to go with the next panelist, but I want to remind the people here in the meeting that we have a Google Doc. If you have questions right now, you might not remember what you wanted to ask at the end. So go and write them down now. So let's move along. So our next panelist is Dr. Donegan, a member of the Scientific and Professional Cadre of Senior Executives and the Senior Scientist for Digital Advanced Materials at AFRL in the Wright-Patterson Air Force Base in Ohio. He serves as the principal scientific authority and independent researcher in accelerating advanced materials development for the Department of the Air Force, including computational modeling, high-performance computing, and applying AI with autonomous materials research systems. Prior to his current role, Dr. Donegan served as the research team lead of the Digital Manufacturing Research Team at AFRL, where he directed the Air Force research portfolio for advanced manufacturing.
All right. Thanks, Juan.
Mhm.
So I'm not planning to show any slides. You just have to listen to me talk for a few minutes. And I want to start by kind of pulling on a thread that Jim started talking about, which is the sort of the primary goal of MGI being to accelerate the deployment of novel material systems. And I want to really emphasize what Jim said, which is it's not just the discovery of new materials, but it's really the discovery to development to deployment pipeline that requires acceleration to actually deliver material solutions more quickly. And whenever I talk about this with non-materials folks, I like to tell the story of titanium aluminides, which I think a number of folks on this call may have already heard before. So hopefully you'll bear with me. But for those who maybe don't know what titanium aluminides are, they're an intermetallic alloy that is flying in real aircraft today, and commercial engines, for example, in the low pressure turbine sections of some both GE and Pratt & Whitney engines. They started flying in these engines commercially in the mid 2000s sort of era. And you've probably flown, if you've flown on any A300, Airbus A300 aircraft, you've probably flown with this material sitting next to you in the engine. What you may not know is that the idea of mixing titanium and aluminum to form an intermetallic was first kind of conceived of and thought of back in the 60s. And it took on order of around 50 years to get that alloy from the discovery standpoint to the operational material solution standpoint. And I really want to emphasize what saying a material solution to a problem, not just a new material. I really think this is sort of the way we have to start thinking as a community, is thinking more about how we can make materials solutions to real world problems, as opposed to discovering new materials or advancing the ways that we manufacture current materials, but the entire chain of developing new material solutions that are of engineering relevance. And you see that with titanium aluminides, because now that we have a robust materials engineering solution, they're used in other places that aren't airplanes. For example, they're used quite a bit in automotive now, high performance automotive. They're also used in watches. Apparently, I discovered this recently. If you want to buy a very expensive diving watch, you can get a diving watch made out of titanium aluminides. That's only possible because enough work has been done to develop the materials and manufacturing knowledge behind the material to make it actionable. And so when we think about, from a DOW perspective, our applications today, it's important for us to really consider the fact that so many of our challenges are materials limited. And developing a potential candidate material is not enough to actually solve a problem that's materials limited. That's a step one of the process. It's obviously a critical process. We have to have the new material to solve the problem. But in order to really kind of take the solution to the finish line, we have to develop the techniques to understand how that material behaves so we can qualify it, understand how it works. And then we have to develop our knowledge to know how to scale it up, source the raw material to integrate it into supply chain, and then manufacture it. These are all problems that need to be solved to actually achieve the MGI goal of material solutions acceleration. And I think the critical thing I want to point out is that the advent of performant AI, artificial intelligence, and our ability to collect tons and tons of data, pass into AI, and hope that some magic pixie dust then helps solve our problems. There's a lot of potential there, but we really want to avoid falling into a trap of looking at those solutions only in the context of materials discovery or only in the context of advanced manufacturing. In reality, accelerating each one of those parts is certainly of benefit. It generates new knowledge. That's not a bad thing. But it doesn't end up solving the entire life cycle of delivering the material solution. The real challenging problems are always going to be at the seams between developing the material and scaling it up to pilot capacity, between going from pilot capacity to a robust supply chain, from going from a robust supply chain to an agile supply chain that can actually be flexible. These sorts of challenges at the seams are really where a lot of our bottlenecks end up arising. And the reality is that we can't really afford to sort of wait for those bottlenecks to solve themselves as they would naturally in the past. The traditional, we end up getting enough experiential knowledge to help overcome a problem to solve it in, let's say, 10, 15 years. We'd like to be solving those problems on the order of single-digit years or even less than a year so that we can be much more agile with how we iterate. I think one of the examples that's resonating with me right now quite a bit is that this sort of requirement to have robust material solutions chains is really evident right now. If you go try and buy RAM, or you go and try and buy a hard drive, for those who are probably following this, pretty much all RAM and spinning disk space is bought up for the next couple of years. And that you can think of as an externality challenge of a material supply chain limitation. We only have, generally speaking, one way to think about creating high density RAM for performance chips, and because of that, if there is some external factor that ends up reducing our capability to source that, all of a sudden we kind of put our hands up, and that's the kind of thing that happened very quickly. Clearly, we don't have a material solution sort of network that can respond to that in the order of the 6 months that problem came about. So that's just one very recent example, but I think highlights where we want to get to as a nation with respect to our capability to be robust to new materials needs. So with that, I think I'll stop there, and I'll turn it over to Andy.
All right. Thank you so much, Sean. And for our last introduction, I'm going to invite Dr. Andy Schwartz, who's the Deputy Associate Director of Science for the Basic Energy Sciences. He also currently serves as the Acting Division Director for Material Science and Engineering and for Scientific User Facilities. From 2013 to 2022, he served as a Senior Technical Advisor for the Energy Frontier Research Centers. And from 2008 to 2013, he was a Project Manager for the Basic Energy Sciences Experimental Condensed Matter Physics Program.
Great, thank you, Juan. Hopefully I sound okay, and hopefully you see the screen, full screen mode.
Yep, you're all good.
Thank you very much. Okay, so thanks everyone. I'm going to try to be quick so we have a good chunk of time for Q&A, because I think the discussion in these panels is often the most interesting part. But I did want to, so Jim, back in his opening talk, did mention the Genesis mission. I suspect that many, if not all of you, have actually heard of the Genesis mission, but I know there's a lot of open questions. I'm going to do a very high-level overview of what my understanding of Genesis is. It is obviously still very much in development. So this originates back in November with an executive order launching the Genesis mission. This is a government-wide mission. It is the Department of Energy that is tasked with leading it. That's Energy Secretary right in the middle. That's our Undersecretary for Science, Dario Gil, and to the right, on the far right, is OSTP Director Kratsios. But this is really, I think, in large part, Dr. Gil's vision and one of obviously his signature priorities as he's come in to this role. So what is Genesis? It's a national mission. As I said, it's broader than DOE, though DOE has been given the lead to coordinate this effort. It's also broader, much broader, of course, for this community than materials, though I will argue that it's many, if not most, national priorities have materials embedded in them somewhere. And so I think that what you'll see as I go through is lots of opportunities for material science research in this space. So the goal here is an integrated platform connecting supercomputing, experimental facilities, AI systems, and data in a sort of uniform, integrated way. This is the vision specifically for science and innovation. So this is about using all the capabilities we have, the new AI tools layered on top of the experimental capabilities, the computational capabilities, and all the data that already exists and will be generated and it's bolded here, this was the stated goal, double the productivity and impact of American research and innovation within a decade. So it's this acceleration theme that we've already heard from Jim and from Sean and from others, reframed under this new mission, but many of the same, very much many of the same concepts that we've all been talking about for a long time in MGI and in other contexts, and now sort of broadened out. There's a series of pillars that have been defined or are being defined, sort of an infrastructure pillar to build the backbone, and specifically something called the American Science Cloud and the AI Model Consortium, or ModCom. American Science Cloud, for those of you who are paying attention, was called out by Congress in HR1 last summer, HR1 also known as the One Big Beautiful Bill. It specifically tasked the department to establish this American Science Cloud and actually provided initial funding for it at that time. Data, of course, underpins all of that. I think this group knows that well. I don't have to tell everyone here how important the data piece is, and lots of opportunities as well as challenges there. And then the models and the sort of, I said challenges, I meant sort of scientific and technological challenges, the S&T challenges that will drive the development of those models. And I'll talk a little bit about that coming up. And finally, what we're calling a partnership pillar. I mean, this in the end is not just the department, and in the end, it's not just the federal government. This is intended as a public-private partnership, and that has been quite clear in the public messaging that has come out so far and will continue to be the case, that a partnership between federal government, academia, and industry is going to be critical for success in this space. When the Genesis mission was rolled out, there were sort of three high-level buckets: energy, discovery, science, and national security. This, of course, is the DOE mission in a nutshell. But it was also made clear that that Genesis, while it would start here, would be broadened out to the whole federal government. And I believe that started to happen. The coordination is happening through the National Science and Technology Council, NSTC, which met, I think, just a week ago yesterday, maybe, or maybe 2 weeks ago. I've lost track of days now, and started to do that coordination. So I think over the next coming weeks and months, you're going to start to see more, not just from the Department of Energy, but from other federal agencies regarding engagement with this Genesis mission. Just a week ago, on February 12th, so actually less than a week ago, there was an announcement of 26 science and technology challenges. This was called out by the executive order that the department was to deliver these to OSTP in January, which we did, and they were published in this press release last week. The links are here, but I'll stick them in the chat. I won't try to multitask and talk and cut and paste at the same time, but once we get into the Q&A, I'll dump these links into the chat if people want to see. But what you see on the right is these some description of these 26, but maybe more interestingly, here's a subset of them that was called out in the press release. Scaling the grid, nuclear data. I should also point out these S&T initiatives span the Department of Energy. So it's the science side of DOE where I sit, it's the applied energy side of DOE, and it's the National Nuclear Security Administration. So you'll see the whole of the department reflected here. Particle accelerators, okay, right here. Designing materials with predictable functionality. That sounds familiar to this group. Subsurface geoscience and geotechnology, autonomous labs, we've already talked about those today, advanced manufacturing, quantum algorithms, there's a quantum systems one as well, microelectronics, obviously lots of material science to be done in microelectronics. And again, this is a subset of the 26 that are in the link that I'll send. So these are meant to define sort of the big bucket science and technology areas where the department has at least now determined are the sort of best opportunity space for applying this new platform combined with the data and the models. And this is a graphic. I won't spend much time. This is a cartoon graphic. Sort of I think meant to sort of say, okay, why DOE? And it's it's not going to get done by DOE alone, but DOE does have the network of 17 DOE labs that own and steward some of the largest supercomputers and much of this a huge store of scientific data. Our undersecretary, one of his sort of the things he keeps hammering home is that he believes we're failing to tap into all the data that already exists, let alone the new data. And so figuring out how to do that better and then make that accessible. So this idea of this American Science Cloud and these models and data that will sit on it is that it's an infrastructure available to the whole community. This is sort of the model of DOE user facilities writ large. So we build and operate major facilities, which we then make available to the broad science S&T community. This will be something of that nature if it is successful in the way is envisioned. Just a couple more slides to wrap before I wrap up. This is not new, of course. We've been talking about AI, particularly here where I sit in the Office of Science, the basic science side of DOE, for a number of years. And I think this American Science Cloud, as you see on the graphic here, is sort of just pulling together all of these different pieces. I mean, in the end, we want, for our purposes, we want the AI to support science as a new tool for doing science. We also innovate in the hardware space, certainly in the computing space. Our Advanced Scientific Computing Research Office builds, supports, and builds and runs the major supercomputers, as well as doing the applied math and algorithm development. Major user facilities, things like X-ray light sources, neutron scattering facilities, et cetera, generate enormous volumes of valuable data. And then developing the tools and training the workforce to use them. And so putting that all together into sort of this integrated platform is the vision that's been laid out here. And then just as a final concluding slide before I wrap up, part of the HR1 last summer did, as I said, provide some seed funding to the Department of Energy to start some projects in this space before, to get things going quickly. And so here, what I show here is two examples from the office where I sit, Basic Energy Sciences, both of which have materials aspect to them. So one is a project led by Oak Ridge National Lab called MakeMag, multimodal AI for 2D quantum magnets, really trying to pull together multimodal characterization data, neutron scattering data, X-ray scattering data, microscopy, and the models to essentially reverse engineer the Hamiltonian for these class of 2D quantum materials. They've got collaborators at a number of other labs, Brookhaven, Argonne as well. And then second, a microelectronics focused project decoding defect-mediated mechanisms governing stability and function, really trying to essentially model the defects in materials as the functional elements of these materials, learning how defects define functionality in advanced materials. This is led out of Argonne National Lab, but again with a number of partners. Both of these were designed. The request for proposals was to pick a problem where the performers believe that within a 2-year period with a somewhat modest budget, a few $1 million per year for each of these projects, that they would be able to sort of demonstrate this, taking data that exists or data that could be collected from multiple sources, building models, and taking those models to apply to a very specific a science problem, and sort of demonstrate this AI advantage in this specific case as a proof of concept, or as we call them, a pathfinder, where you could then build upon that for the larger platform. So I think that's my last slide. So I'll stop there, turn it back over to our organizers to moderate the Q&A. Happy to take questions.
All right, thank you so much, Andy. So with that, we are done with the presentations for our panelists. So we're gonna go into the Q&A. As a reminder again, if you have not joined the Google Doc, please go ahead and add some of your questions there. But let's start with some of the questions that are already there. I don't believe that the questions are directed at any particular panelist in the way that I'm gonna phrase them. So if anybody has something to say, feel free to unmute and we'll try to keep it as organized as possible. So the first question here is one of the questions that we have in the Google Doc. So across your agencies, what do you see as the most important shifts in how materials data and AI will shape national research priorities in the next 3 to 5 years?
Want me to take a crack at it? Then my colleagues can jump all over.
Go for it, Jim.
Well, I mean, I would say that, at the risk of sounding like a broken record, because of the broad acceptance of the importance of AI, data is now viewed as the rocket fuel for all of this. So, I mean, it's way beyond lip service now. I mean, I think it's just broadly understood that while we were very, very early to the party, there's not a lot of credit for being right too soon, but at least we, have walked these trails for some period of time. And I think, again, this community is well poised to attack some of the broader issues.
can I jump on that a little bit, Jim? This is Dave.
Sure.
I think you're exactly right. I think that we've always had this issue of sharing data and the idea that there is IP and value in materials data, but that's just sort of jumped to a crazy another level, right? And so we have new companies that are making data that will remain proprietary to them likely. And we have new concerns that not only is the data more valuable than ever before, and so those who are working towards thinking of projects that create that data have some concern about that. We've talked about that in the FAIR and open science community. And then we have concerns about security related issues and what data goes across the world. And, so the question is sort of, do you think about, or do members of this panel think about, like, what's the right data to be open, to be pre-competitive, perhaps? Or is all data open? Or are we actually going to be struggling harder to get people to share data in meaningful ways?
Well, I'll take a crack at it. I don't have any great answers. This is a huge part of the dialogue, though, that we're having here and really across the community, of course, is because a lot, as Jim said, what did he just say? It's the rocket fuel, or it's it's what keeps it going, right? I mean, none of this works. None of this works at the level we would like to see it work or think it can work if the data isn't there, right? It's, in the science world, we keep telling people you can't, it doesn't matter how good your model is if the physics isn't in the data. If you don't have you're not going to find the physics in the data set if it's not there, right? The models can do great things, but finally the data is really important. So this question of sharing for what purposes, right? I mean, what are you doing with the data? Who has access and what will they do? It's a huge challenge we are faced, not challenges, right? It's a huge part of the dialogue here at the department, because we do have, again, within the complex, an enormous amount of data, some of which has been generated by, let's say, DOE lab employees, DOE lab staff, but much of which has been actually generated by external users using our facilities. And then there's this whole question of, okay, so what does that look like? And what does it look like locally at one facility? What does it look like if you try to look across, look at multiple facilities or across multiple labs? That, I think, has to be, I think that conversation has to happen. And I'll say one more thing and then leave it for others. It's a combination of sort of the formal written agreements and sort of community culture and acceptance, right? So there's plenty of examples of cases where the Department of Energy and the labs at which the facilities sit actually have quite as written in the agreements, have quite extensive rights to the data that has been generated by users. But depending on the field, the expectation has been historically that with some that the user owns that data, so to speak, right? And there's so I think we have to manage both of those pieces of it, sort of the formal part of it, but also the informal. And I think we see it in certain communities moving where people recognize, oh, there's actually real value in sharing my data with others and vice versa. And I think if we have to find ways to get there. It can't be just only the sort of stick part of it. You have to share kind of thing. I think that's not likely to be, my opinion, not likely to be successful broadly, but building the mechanisms to do it easy, to make it easy to do, and also to make it where an individual researcher or groups feel like there's value in doing so, I think is a really important component. I'll stop there.
Thanks.
So, I mean, I agree with what Andy said. I'll just say a word or two maybe from NSF. I mean, many may remember the harnessing data revolution big idea that we had several years ago, and I think that kind of shows that NSF was thinking about this a decade or so ago, and there was some progress made under that, I think, with respect to data. But now that that's a little bit in the rear view mirror, I think that we are seeing a lot more emphasis at NSF, thinking both about really the data issue and the use of AI. So I mean, those are coupled, but they're somewhat independent. And so I mean, we have various working groups on both of those at NSF on thinking about what should be required with respect to data and data availability, accessibility, curation, all those sort of things. How that might change, with time, about how the way we thought about data curation 5 years ago might be different from what we think about it today with AI tools being available, et cetera. And so, NSF is making new changes to things like the data management plan. I think in April that there's going to be new guidance as to really how the data management plans will be developed and submitted at NSF. So that'll be a change that's coming. Also, requirements for timeframes for when data will be made available. That basically, when you publish a paper, the data that that went with that is now will be required to be made accessible, useful to the community. So I think that it's recognized that this is critical and important, and I think that for sure additional resources will go into really both sides of that problem. And I think that having community feedback, such as we would get from MaRDA on really, what the community feels are the best avenues to implement this, will be important. But, those of us at NSF will be thinking about ways to promote this. I guess, from both sides, again, from the stick side and the carrot side, that, we will, try to make sure that PIs adhere to what they put in their data management plans, but also, be able to make resources available to encourage the community to think about these issues. So I will stop there, but I think it is something that certainly that the new NSF is taking seriously from various perspectives.
I'll add one more thing, which just I think will add just another layer of complication to the matter. But one thing that I've been thinking about quite a bit, especially over the past few months, in the context of the proliferation of autonomous experimental systems or self-driving labs, is in the not too distant future, I imagine we'll be in a situation where we're generating far more data than we can have humans looking at effectively. And as a community, and especially from my perspective from the defense side, are there going to be areas of materials properties that would traditionally fall in sort of the export control list, or something that we wouldn't want to be broadly publicly available? And what's the mechanism for putting guardrails around these types of automated systems that are just generating far more data than we'd ever be able to manually interrogate or assess? I think there are some design questions there from the perspective of how we build these data generation systems and how we connect the pipes between them to allow users to share data. So it's just an additional facet of the problem that we can think today about the data that we have and potentially apply the sort of the rules that we have for our current menu of data, but then coming up with some mechanism to think of that in the context of systems that are generating data without the human aspect of having to load up the data and add metadata, all this sort of manual effort that allows for checks, if you will, on the value of the data. There, I think, will need to be some conscious assessment of those types of systems to make sure that there's not generation of information that's whose value is so great that we wouldn't want it to be shared, or the number of parties that we'd want it to be shared with would be a limited list. So it's just an additional facet to the maybe the good problem of having too much data.
Yeah. Let me put a bow on this then, because there's what's interesting, Dave, is based on the question initially, is I think the conversation has moved on the incentives. Okay. What we're hearing now is, well, how do we keep other people from getting my good data, right? In other words, so everybody wants the data now. So the incentives are completely different, right? So there are really IT security related questions. How do you decide, make decisions, assess these things? I mean, so there's a lot that this community now suddenly can really dig into in terms of the infrastructures, what kind of AI tools are we going to bring for curation, which I think is actually really going to really help. And, what are the challenges for the academia in particular? Not so much around data security as much as how do I optimize, again, so I can write more awesome science right? How do I get the tools that I need to do the next great pile of research? And if I can't get access to data, how am I demanding of my government, right, the resources to flow in ways that allow me to get access to that data, right? So, it's one of the encouraging things written into the text for the founding documents for Genesis is the sort of public utility aspects of it, for lack of a better word.
Right. But each agency has a different mission and will see governance with a different lens, is all. Right?
Sure.
But I think that data governance broadly makes fair more important than ever, because the only way to have governance is to have visibility that you can then automate that governance, right?
Or you could just balkanize and have a whole lot of different policies. That would be another choice.
That would be one. Yeah. I'll leave that to you all who do that stuff. Cool.
Remember,
Juan.
Jim, you're being recorded.
Did I say something wrong?
Worse than that, he's being transcribed.
All right, so I'm going to combine a few of the questions that we have here, and I think I had said that they are not directed at a specific panelist, but I think people took that as actually pointed to someone. This is a question for Andy about the Genesis missions. So as universities think about aligning with the objectives of the Genesis missions, how do you see the role of the academic teams? So PI-led fundamental research and like the early stage ideas. What do you think that role is? And what, in your view, would make an effort truly mission aligned?
Okay, that second half of the question is harder, so I'll check the first half. But so there's no doubt, and that we in the success of this mission is gonna, as I said, it's sort of an all hands on deck. We need there's clearly been focus in the first whatever it's been a few months of this initiative on the national labs, and that in part comes from our congressional appropriators, and in part from this mandate that DOE kind of stand this up. And I think it's a good starting point. This network exists, but it's been clear from the start that this is not just about the federal government, not just about DOE, and not just about the federal government. That the academic partners and the industry partners are super important part of this. And there's a whole team within DOE that's just talking about partnerships and sort of how to engage. So I think the academic researchers have a huge role to play. I think in the near term, it's going. I can't really speak to details, but I think you're going to start to see in the coming weeks, maybe even, or months, small numbers of months, some opportunities for more direct engagement. There is actually an event being held. The department is hosting an academic / philanthropic summit tomorrow. It was being hosted by our Undersecretary Gill, where they've invited a number of research leaders, so VPRs and those kind of thing, people and others from the academic institutions to a sort of one-day gathering in near DC to sort of brainstorm some of these, exactly the kind of ideas that the questioner was asking about. What is the best way to engage? What would be most valuable from the, let's take university side? How does that fit in with the national lab and industry pieces? So I think looking for the opportunities to partner is certainly going to be seen as a positive in this space. That's not to say that there's not lots of good research to be done in one or the other sector still. So I think it's got to be a combination. And look, a lot of these things, this is not brand new, right? People have been working on these things for quite some time, looking for the ways to sort of to engage with this bigger effort. One, hopefully for benefit of your research, but also to be able to sort of share where you think the opportunities are and what would be most valuable for you, right? As we build out this platform, which again, it's a big vision and it's a big challenge, but making sure that there's input from those who eventually will be the sort of users of it and the is really important. And so looking for opportunities to do that. As I said, there will be some opportunities coming in the relatively near term to actually solicitations for proposals in this space that will engage broadly the community beyond the DOE. So I just keep your eyes open for those. And more importantly, thinking about how to again, what you see as sort of what's working, what's not. And then I guess the last thing I would say, and it's something we've been thinking about a lot here, is to picking the problems or the science. Okay, come from a science perspective, but let's say S&T broadly, picking the right problems, at least in the near term, I think is going to be really important too. I mean, there are going to be certain problems that are sort of more ready for this kind of approach than others, I think, and those of you who are working in the fields know that. And so, this is not going to be a sort of one size, in my opinion, this is not a one size fits all. We build one thing and it solves all problems. And it's also not, some of these things are going to be much more challenging. And there may be certain science and technology problems that are not particularly amenable to a large data AI approach, and that's okay. But for this particular effort, let's pick the right problem so that we have sort of increase our likelihood of success.
All right, I think that's a good answer for that, because I believe that the questions wanted more details, but I think you covered it pretty nicely there. And one of the comments that you made actually tees up the next question pretty well. So we have 4 different agencies right here today. So as these large-scale challenges move forward, how do you see coordination happening, both across funded projects and potentially across agencies, to ensure that efforts build a coherent and interoperable ecosystem of data and AI?
Boy, that's a setup question. That's a great question. I mean, so obviously the MGI has coordinated across the agencies for the whole life of it. It's the whole point of it in some sense. That's all that the MGI in some sense is agency coordination. We, of course, are actively engaging with across the federal government right now to try to broaden that coordination really to include everything in materials. That's an ambitious activity, but we're trying to find the right modalities for doing that. And then, of course, we all have our missions and our stakeholders, many of whom are represented here. And we're, of course, obligated to coordinate with them as well. But we're trying, right, to sort of maximize efficiency. Resources remain constrained, and we don't sort of see that particularly loosening anytime soon, although there will be priority areas that do better than others, as there always are. So, I mean, I guess what I would say is we have lots of experience in coordinating. We're doing our best. We welcome feedback, and we're going to try to. We think this is a super important area. As you looked at the priority areas for Genesis, for example, or just in my own agency, you'll see it's a lot of material stuff that those are the priorities. So I think materials data in general, front and center.
Maybe I could just make a quick statement there too, is that, I mean, we have I had mentioned in the presentation I had is the MGI PI meeting that we have that brings together various MGI related activities from various federal agencies. And certainly from the DEMREF perspective, I mean, we've made, encouraged our PIs through various supplements to find partners among other teams and also across various federal agencies. And so we, actively encourage our PIs to reach out and work with the national labs and federal laboratories. And we have our strong spots and, our strengths, and we'd like to be able to couple those with the strengths that the other agencies have. And so by bringing the PIs together at various meetings and I think making some resources available, we've seen indications that can multiply the impact of the science dollars that we have. So.
All right, I think we have time for maybe one more question. This is 2:20 is when the panel ends, and I think we've had pretty good discussion. So I'm going to try to make a question out of, there's quite a few questions that I'm going to invite the panelists to, after the panel, to go and see if you want to leave some comments there for the people that are that might not get their questions answered live. But the question that I think would cover most of the remaining ones is about data, because this is MaRDA. So as automation and AI-driven experimentation continue to scale, they will generate increasingly large and complex materials data sets. How are agencies thinking about infrastructure to support this? This would be standards and sharing frameworks and incentives for people to share their data. And how could we use those to ensure that the data is fair at the end and can meaningfully accelerate discovery?
So I don't know if Ben Blasic's on the line. I know he's on the governing panel, but NIST is a longtime supporter of Materials Data Facility. I know DOE is home for a lot of the resources that support that. And I know there are lots of others building out their own internal infrastructures in certain cases. Super important, only getting more important. Making stuff fair is still not trivial. And if you figure out that it is trivial, please let us know. That would be good. So I think we understand it's super important. We also understand that there's sort of always this hierarchy of need that drives a lot of the decisions, and sometimes data is not baked into the initial conversations, and that's a mistake. So I think the more that we get people like ourselves involved in the conversations earlier, the more likely it is that things will go better on this front.
Yeah, I don't have much to add. It's hugely important to think about it and to do it, and to, as sort of I was alluding to earlier, make it, sort of bring down the barriers, make it easy, right, for people. People are gonna, but it's not easy to do. I mean, think about how we build in all of these agencies build incredibly complex, physical infrastructure. This is partly physical and then partly sort of, and it's really challenging. I think, but we have to just keep chipping away at it, right? We have to do it at a small scale and demonstrate it at smaller scale, build it up into larger scale. And there's examples, right? There's I'm going to use the one I know. There's the materials project at Lawrence Berkeley National Lab that we've been supporting for a number of years that has, started out as a Berkeley only thing. And now now they've built in this MP contributes mechanism for others to contribute their data, and a shared agreements as to who owns what and how the data gets put, and also making sure that data, is as close to fair as we can get it, but is accessible, has the relevant metadata with it, is, valuable. So those, and I'm sure there's other examples, right? Those examples exist. If we, maybe let's start putting together pieces of the puzzle and building bigger networks, and start to think about how you want it. It's, look, I'm far from an expert. Those who know this and work in this world know it much better than I, and will come up with better solutions. But I think that, and the other part of this conversation that actually I was in another meeting just last week, not specifically about this, but about, superconducting qubits, and this question of how do we share the data of all the data that wasn't the successful published data, right? I mean, it's really important to know what people tried and didn't work, is almost as valuable maybe in this space as what did. So we're not recreating efforts, but that's a whole nother level of challenge, right? How do you, move into that space? So it's just something we have to work on collectively. I mean, we have to work locally and institutionally. Certainly from a federal government perspective, DOE does have some plans in this space, particularly through our Advanced Scientific Computing Research office. This is something called the High Performance Data Facility, which is, very early stage plan, but it's a plan to build a, shared data facility that would, integrate with the high-speed networks and the compute that we have in a way that, answer some of these questions.
So I'll follow on. I think Jim and Andy pointed out some great examples of success stories with, or I'll say models for how the agencies can fund the development and kind of the stand up and development of data repositories like MDF and Materials Project. I think something that I've come to terms with over the past few years is that materials data is so varied there's not going to be a one-size-fits-all solution. There's not going to be a single US Center for Materials Data for all materials data to go into. I just don't think that's going to function. There's just the variance in data is too broad. The kind of data, the velocity in which it comes off the different systems, if it's coming from experiments or simulation, there's just no way to come up with a unified system that's going to have all of it. I think the other kind of flip side of that is I don't think we as a community should spend our time thinking about coming up with a unified data standard for materials information. That doesn't mean we shouldn't think about what it means to have pedigreed data and what are the standard kind of meta tags we need on it to make it fair. But I don't think we should try to twist ourselves into knots over what should be the standard definition of an electron microscopy image. Speaking from personal experience, we went down this road just between Army, Navy, and Air Force some decade ago, and it ended up being not worth the time after the end of it, what we came up with. So I've come to terms with the fact that instead what we should focus on is kind of what Andy said, which is what are successful models to storing data and making that data fair, that have worked in different places, and amplify those across the community to essentially challenge performers who are generating data to look at those models and come up with a solution that works for them that abides by the success of those models. Not prescribe, it's going to fit to this very stringent and predefined standard and data sourcing location, but more needs to adhere to these requirements, FAIR being obviously a very good one to start with, but not just saying adhere to FAIR, also saying here are examples where it's worked. If you can't figure out how to do it, and then I think the onus is on, from the interagency perspective, to have a clear message story of what are good ways to do things that have been observed to work well, so that then we can come back to performers and say, here's a menu of potential ways to think about the problem, to really help kind of get the community moving in the right direction. Because like Andy said, this is going to be a chipping away at the sort of problem. We're not going to, it's unlikely we're going to get a massive influx of the required capital to build out this, some unified solutions. So we're going to chip away at the problem. And from an interagency perspective, we can provide examples of how that has worked. And I think that's just going to have to be our mechanism for moving the ball forward over the next few years.
Yep. I think that's a good way to phrase a good end to the panel as well, where we restate the importance of fair data, and we have the perspective of the agencies on how that can be achieved. We are surprisingly still on time, but I believe that Selena has some instructions for waves that
Juan, I'm gonna jump in for 1 second on that wrap. Thank you, and thank you for that moderation. I want to thank all our panelists again, and give everybody a chance to thank them again. Sean Donegan from AFRL and John Schlueter from the NSF, Jim Warren from NIST, and Andy Schwartz from DOE. That's a super important panel for us and for the community to hear, and to start all kinds of new conversations and continue ones we've been having. So we really appreciate that. Thank you very much for that time and that openness. I'm also going to take advantage of that last question to point out that session 6 of this very meeting, Thursday afternoon at 2:25, is on AI-ready data, materials data repositories. So really a question that comes up about FAIR and about repositories and about how we handle this. We're going to have 4 very experienced people talking. Ale Strachan from NanoHub is going to talk. We're going to hear from OQMD from Jacob Pietra, and Owen Price Skelly is going to talk about Materials Data Facility and this new CSSI project Garden, on accelerating things. And then we're going to get a European perspective from Joe Rudzinski, who comes from Nomad and the FairMat project, which has been producing sustainability by rolling out Glade, where they actually install Nomad in other places. So we're going to hear that perspective a little bit. Jane Greenberg from the MaRDA Council.
Thank you.
Matthew
Thank you
Evans.
for saying something about it, David.
Yep. So that's going to be a great place. We're not going to take time now and talk about it, but MaRDA is thinking about all these things. And by MaRDA, I mean our community. So that's like sort of a great advertisement for that. But now we are going into a poster session. I'm going to let Selena make sure everyone knows how that happens. We come back from the poster session to start our, our next panel discussion at 3:30. That is also a great panel. Ben Blazek will be one of the moderators, along with Jake Yeston and perhaps Kate Brinson, on this material industry connection and the emergence of data-driven AI. But Selena, would you get everybody off to the new poster session, please?